Good afternoon, everyone. My name is Vaibhav Gedigeri, and I am a lead data scientist for the TIBCO data science team. Today, I will be talking about accelerating innovation through hyperconverged analytics. So without further ado, let's jump in. It's just a standard disclaimer. So let me just briefly go over the agenda of what we'll be covering today. We'll start off with just talking about what this convergence is between analytics and data science in reference to the Gartner white paper. We'll then jump into what is hyperconverged analytics. We'll also talk about the collaboration among personas, and then we'll jump right into the enabling technologies behind hyperconverged analytics using our data science stack. And then we'll jump right into some demonstration where I'll show you some two cool examples that we have here, and then we'll close the talk with some takeaways. For any of you who have questions, I have created a breakout room. So once the session ends, please feel free to get on the breakout session, as I will be there, and I'll be more than happy to answer your questions. Okay, so Gartner published a white paper earlier in the year where they talked about this collision of the data analytics world and how analytics and BI are colliding with data science. As you can see here that there are different personas, and you can see here that intersection of augmented analytics. So analytics is colliding with business process management and applications. You have citizen roles that are colliding with traditional roles of data architect or application developer. But we here at TIBCO feel that this convergence is not only in just one of these areas. We feel that they're kind of there's convergence among all the other places within the data science lifecycle, and hence we feel there's more of hyperconvergence per se. So what is hyperconverged analytics? We start with data and process management, where we simplify data exploration at rest, streaming data in the cloud, on-prem, or at the edge. And then we derive insights from visual analytics, and then take actions on event stream to finally do data science for learning. And this closed loop decisioning type application is generating a lot of value across a lot of the domains that we see here. Now, when we talk about this collision or conversion, I'd like to break this down and see what are these personas where we see this convergence, and kind of relate it to the data science stack that we use here at TIBCO. So we have our visual analytics environment, which basically allows users to do data exploration, wrangle the data, and gather insights from it. And then we also have our typical data science stack, where we have data scientists, data engineers, developers working on this platform to do data prep or even model building through these visual workflows that can run at scale. The data scientists can decide to even write code in a notebook environment and hook that up into that visual workflow. And then you also have the ML engineers who then take this work, these model objects per se, and then they configure these interfaces for the business analyst, for the data scientist. They interconnect systems. They develop these streaming workflows if it's a real-time use case, and eventually even perform model operations. So as we can see here that all of these, as you can see here that our visual analytics platform can directly call into our data science platform, and vice versa. So let me jump kind of jump into the enabling technologies behind this hyperconvergence and what's driving hyperconvergence through our data science stack. So we'll start with the visual analytics tool. As I mentioned, Spotfire is a tool that enables users to do data exploration, data wrangling, and even in some case, even perform data science related activities. And one of the features that enables this is the function of a data or data functions by itself. So in Spotfire, we have the feature of data functions, which enable us to directly call into our TIBCO data science platform to run big jobs. We can run this from a button, or if we have configured the parameters, we have used an analysis. The data functions can be defined in any of the Spotfire applications. They can be a mix of different types of data functions, R, Python, and so on. Data functions can run automatically. So when you refresh the data, or if there's filtering that occurs, data functions can also be triggered by the user, and they can also be chained and cached. So let's dig a little deeper into how do you configure these data functions inside of Spotfire, which enables us to call into even our typical data science platform. So each data function has a defined set of inputs. Now these can be tables, vectors, and values. And each of this input is actually accessible as a variable in the code. Now, there are ways of defining inputs, and these inputs can come from many sources. So the inputs don't really only have to be tables, vectors, and values. They can be document properties. They can be custom expressions, or they can be set interactively using text area controls. So, so the outputs of a data function, they can again be a table, column, and values. And data functions also automatically map variables from code to geospatial outputs. So looking on the right-hand side here, I have fit a self-organizing map, which is a form of neural network through a Python data function. So in this case, what I'm trying to see is a structure in geology in energy or seismic type application. So now that we have kind of understood like how what is that feature that enables us to communicate to our data science platform, we also have infused AI right inside our visual analytics platform as well, right? And let's take a look of how we have done this. So here's an example where I'm trying to analyze a vehicle data. And let's say I'm interested in a variable that I want to explore further, and I want to know what its correlations are with the other variables in the data set. So in this case, I'm interested in knowing more about miles per gallon highway. And when I click on that, I'm trying to analyze the fuel efficiency of a set of cars, and I can see there's a relationship with miles per gallon in the city, vehicle size, engine displacement, and I bring them on to the canvas. Behind the scenes, Spotfire has found these relationships and presented them in thumbnails in order of strength of the relationship to the variable that we're analyzing. Now, if you see, we can click on these individual points to reflect filtering in the other charts. And let's try and look at some outlying points here and select them. And if I click on that, and we can select it and click on a bulb and look at what those cars that have high fuel efficiency, we can also notice there is a relationship with engine type, transmission, and so on. And I can take this and bring that into the canvas and see that it's the hybrid or electric cars that have high fuel efficiency. Now, all of this just happened really, really quickly. And I have been suggested the relationships through an inbuilt AI engine, explored the data to find the relationships and found patterns in it. And this all happened just through a few clicks. Now, I would also like to jump into the data science side of the equation. So here we have our typical data science platform, this platform allows us to build visual workflows by dragging and dropping the operators on the left, and to run these workflows at scale. So with absolutely no coding required. So these operators on the left, as you can see, we have multiple operators ranging from loading for data, for transformation, and even prediction, which involves calling out multiple models. So let's take an example here and see how this works in action. So here I can join up different data sets. And in this case, we have implemented automated machine learning. And so I can go ahead and drag the AutoML orchestrator. I can run that. I can choose the dependent variable here, and it's a set of financial transactions that predict fraud, and run the workflow. I get back a set of workflows that analyze these data, which also shows a leaderboard on what the best model is. Now, looking at the summary, these individual workflows have been generated for me, which are data preparation, feature engineering, modeling, and all of these are actually fully transparent. Now, I can go and edit any of those. So let's take an example here. In this case, I want to go and edit the modeling workflow by adding a resampling operator to upsample the fraud cases. And I can go ahead and hook that up, and I can rerun the model. Now, what I get back is also an explainability analysis. What are the important variables that are, oh, I'm so sorry about that. All right, so what are the important variables that are driving fraud? We can see credit score is a big one, followed by age, and followed by income. Now, I can also look at correlation structures between the variables. For example, income is an important variable, but it's also correlated with age. Now, let's say if I click on age, I see the correlation with credit scores, and I can see orange. So the orange squares are where we predicted fraud, and blue is where we did not predict fraud. I can also see where I was able to predict fraud, typically at the low end of the credit score for a particular age band, in making those predictions, and predicting no fraud at a higher end of the credit score for each of these age bands. The size of the square is a support for that combination in the data set here. Now, once we have this, we can also go ahead and create these parameters where we have this, where we can go and relax the data size limit. Now, when there is a low data support to eventually get those points on the graph, to see the correlation between age and credit score. And we actually notice that the model is doing pretty well. So on the chart on the right, you can see the credit score is on the x-axis and the age on the y. Now, what we get back is basically a modeling workflow, an explainability workflow, the correlation between the variables. I also get a scoring workflow, which is right here. So I'm sorry about that video lag. So I also get this scoring workflow, which is fully operational. Here I can take this right into our risk investigation application. So someone here can create a case when there is a suspicious transaction, and then assign a case manager who can then manage the case to completion to finally determine whether this is a fraud or no fraud. Eventually, once we have come to this conclusion, we can take the result and incorporate it back into our training set and update the model. So far we have seen how we've infused AI into our visual analytics tools, Spotfire, and we've also had a look at our typical data science platform and how we can build visual workflows that run at scale. Now, the next part of the lifecycle is model operations. So let's take a scenario here. So the data scientist prepares and trains, let's say, a propensity model with the TIBCO data science platform. The data scientist provides the trained model, and then you have the ML engineer who packages, tests, and deploys the model as a service running on a scalable compute cluster. The data scientist improves the predictions and pushes the new model to the model operations, and this process is pretty iterative. You will have a developer that would finally manage the models, monitor the models, look at the performance in changing conditions, and then basically update and refresh the models at a specific frequency. Now, this is all happening at the back end. In the front end, we have a web storefront that calls the service to determine whether to present the discount to a customer or not. You also have a customer service application that calls the same service to determine whether CSR should make an offer to a customer. Now, moving on, in addition, cloud services play an important role. Ability to tap into these machine learning services provided by the cloud vendors through Python SDK greatly extends our data analytics palette. So here in the middle, right here, we have the cognitive services catalog from Azure, where we grab these pre-trained and pre-canned solutions or containerized versions of these models to be used in an edge scenario. Now, we can invoke these services inside our TIBCO data science platform, or through a notebook environment, or even connect them to individual workflows. We can even call them inside our visual analytics tool through our Python data function feature that I just showed. So let's dive straight into the examples here. So here we have a video feed or a video camera in Alaska that's always on a stream. We take a sample of this every 10 seconds, and the data is then stored in an S3 bucket. We invoke the pre-trained model from Amazon Recognition with a K to detect what's in the frame. Is there a bear or a bird or so on? We can then aggregate this information and then land it on a bar chart, as you see here. So the brown section that you see here at the top are the bears, and the green section are the birds. Now, if you notice this all happened really quickly. The image is grabbed, it's dropped in a bucket, and then you run the recognition model against it. We make a REST call to the model through the Python data function feature, and this returns a JSON dictionary object, which is then further parsed and pre-processed to generate these appropriate visual. This is all interactive visual analytics against a video feed. Now, similarly, we have another example here where we are looking at text data, particularly trying to understand the sentiment of Airbnb reviews. So as you can see here that we are using services from both AWS and Azure. The reviews are written in different languages, English, Spanish, or so on. We are pointing these pre-trained models from Azure and AWS against those reviews to get back a sentiment. You can also see that sometimes the pre-trained models don't exactly agree with one another. And for instance, if you look at a review written in Spanish, it is first converted into English through a translation service, and then the models run against it to give us a sentiment score and a magnitude. We can also train our own models through open source libraries like NLTK and Spacey, and we can also see that we have automated some of this inside our TIBCO data science platform, especially to tokenize the data or even to perform word-to-vector analysis. Here's another example of anomaly detection in a completely edge scenario. So what we see here is we're basically looking at equipment sensor data, and we are trying to detect anomalies in a variable that we're interested in, which is production per minute. So we do this by, again, calling out the pre-trained services from Microsoft which is the anomaly detection, and key phrase extraction. And these are all containerized services. And as you can see that once we detect the anomalies, we also have the ability to kind of get into the root cause of these anomalies. What drove the anomalies in production per minute in that specific time window. We can also further analyze maintenance log files through key phrase extraction to finally come up with a recommended solution, which is, in this case, as you can see, which is kind of replace a sensor. So these were just some of the examples. Now, tying this all together, inside of TIBCO data science, we have the concept of Workspace, where someone can build a data science workflow, drag and drop workflows, and run it at scale. Other developers can also collaborate, for instance, and write some part of this analysis in a Jupyter notebook, per se, which can then be hooked to this workflow. Someone can create this Spotfire analysis, or someone can create this streaming workflow. And all of these folks can collaborate together to build a complete, smart, and intelligent application. Now, I want to go ahead and actually jump into some demonstrations. So today, here I have with me Colin Gray, who's one of my colleagues in the TIBCO data science team, who will be talking about F1 simulation.
To build a data science model, we first must really understand the data available. So with our Formula 1 simulator, we have a lot of data available that we can explore. Here you can see on the left all these different attributes that are recorded throughout the lap. Here we've got graphs looking at statistics such as a rolling average and a cumulative sum. And in this case, we're looking at speed. So this is the speed of a driver throughout the lap. The purple indicates somebody who's going much faster, who does a much faster lap time, and the white or grey, which is slower. We can even look at this to see distinct patterns of purple, where it's clear it would be good to differentiate fast from slow drivers. We can use other simple graphics, such as this box plot, where we can highlight the distribution of speed that a fast driver has here on the left versus the speed distribution of a slow driver. So this way we're trying to differentiate ways that the data can predict a good from a slow driver. But there's a lot of information here, lots of different statistics, and some it's very hard to differentiate the purple from the white. So a much better way to do this is actually to employ machine learning and data science. So what we can do here is we can take that same information, but instead pass it to our TIBCO data science tool. We can pick our track, Melbourne in this case. We can set how many laps we would like to analyze. So let's put in the first 20 laps of the race. And how many random forest trees. So random forest is a type of machine learning model that builds trees to predict things. So let's actually build quite a few of these trees and do a really in-depth analysis of these laps. Simply click that button. And now you can see from the spinning icon, it's going to go away and analyze all the data we have. We split the data into 3 parts. Sector 1, 2, and 3, and that's because all Formula 1 tracks are separated into these 3 sectors, and it makes sense then to model each sector separately. How does that machine learning model work? Well, in TIBCO data science, we can drag and drop these nice workflows without the need to use any coding at all. We can pull our data and gather it. We can generate what we call our features, which is our rolling averages. And then we simply use these 3 model nodes, which are going to take the data split by each sector and build our random forest, which will output the results we see then in Spotfire. So our machine learning models have finished their assessment of each sector, and now we can see the most important variables to do predictions with. And that will make it much easier to build effective models by only concentrating on these values. And it's interesting to see each sector a different set of variables. Both sector 1 and 2, engine temperature is very important, but lap distance, not surprisingly, in the last sector plays a key thing. And we can use all these information to build good predictive models. So let's actually look at how we build those models and how we assess how well they predict. So this is our workflow built again in TIBCO Data Science, where we've dragged and dropped all the nodes to create our machine learning data science workflow. Again, we collect the data and we generate our features. But now we're going to actually build some models to predict the lap times for future races. So we split by sector, and then we split into train and test, so we can train the models on one set of data and use this unseen set of data to predict and see how good these models actually are. We'll build two different models, which can easily be configured all through an intuitive user interface, and then test which of these models actually performs the best. And we can copy and set our interesting information we learned before from a feature selection by picking out the most important features that will build a predictive model. So once we've built our models, we can analyze them and see how well they do. This is a very important and traditional task in data science. You must assess the quality of your models. Are they going to predict and therefore be useful to look at future events? Traditional methods of doing that are coming up with simple statistics to summarize your model's performance. One such way is called an R-squared, where 1 is perfect predictions and 0 is very poor. And here we can see our different models per sector. They've got OK R-squares, and they improve as the laps go on. And we can also look at the residuals. The residuals are the difference between what the model predicted and what the true value was. So in this case, we're predicting how many seconds to finish the lap. So if the residual is 8, that means the model predicted 8 seconds slower or more than the true final lap time. So that gives us an idea of how far from the truth our models actually are. The big problem with using these simple statistics for any model, no matter whether it's Formula 1 or not, is they really hide the truth and the information about your subject. And our subject is racing. So let's look at the models in the context of racing. So these lines show the residual of the models throughout the lap from beginning to end. The green line shows the final lap time. So the closer the blue line is to green, the better the model is in theory. So let's look at a couple of example laps to see how the model did. So this is an interesting lap. You can see that it's very far from the green line, so it's got a big minus. That means it's predicting a much faster lap time for the first two sectors. But then suddenly, the driver makes a mistake. This red line signifies that they went off track, and the crosses signified they damaged their car. And that's really interesting because what you can see here is the model starts to predict an upturn, and that means a poorer lap time before the accident actually happens. And we can use Spotfire here to highlight this and look at what happened. And here you can see where the lap time went down. They actually came off the track and clipped a barrier. That meant their car was damaged and they couldn't go as fast. And the models have reacted and adjusted. And by the end, they're predicting very close to the lap times. If we take another lap here, you can see that it's at first the models struggle to get the perfect lap time, but for the majority of the lap, it's actually very close. Because there's no red or lines or crosses, this driver did not make a mistake. So here you can see for large sections of the lap, the model's very accurate. So if we took the R-squareds of these two laps, you would find that the R-squared of this lap was very, very low, i.e. that simple summary stat would tell us our model is poor. But it's hiding the truth of the matter. And the matter is that up until this point, before the crash, the person's lap time may well have been 14 or 16 seconds faster, but they made a mistake, and that dramatically affected their lap time from here on in. So it's really important to take the context and analyze what your models are saying, put them in the domain of your interest, which in our case is Formula 1, and really see what they're doing. Because what we've learned here is that our models actually can anticipate mistakes before they happen and really respond to them very well. So despite the low R-squared for some of these models, we think these are really good models for predicting Formula 1 lap times in our simulator.
Okay, so another way of understanding and unpacking the model is the explainability of the model. So Here, we have an extension to the analysis that my colleague Colin did. And now we're going to look at the predicted variables, or what are the variables that predicted the lap times. So the size of the dot is the effect of the feature, and the line joining those are the interactions between them. And as you can see in sector 1, there's factors in Brazil versus Melbourne. And now we can also even go ahead and limit this by sectors and a specific lap, in this case, Melbourne. We can also see this across all the 3 sectors. We can see fuel tank for sector 2 and engine temperature in sector 1 having an important effect. So we can look at the predicted variables and their interactions across different racetracks and sectors and what's driving the lap times. So to wrap up what we've seen, the first part of the analysis is in our visual analytics platform in Spotfire to explore the data inside of the Spotfire application, looking at lap times, speed, track sectors, etc. We then call into a TIBCO data science platform to analyze all of the data, the big data, and predict the lap times as a function of sectors and other features. The final model developed can then be taken out and then put into operation. Finally, we then again go back into Spotfire to do some explanation of the model. So another example that we have here is an extension, again, to the same Formula 1 analysis, where we could predict the lap times on event streams, for example. We understand the model, and we can wire up the data coming from the car, and then we can start to predict the lap times or even other attributes in real time, like tire temperature or roll angle, etc. So another cool example that we have here is in drug design, and specifically translational medicine in particular. There's plenty of data out there that looks at sequencing of different people who have varied environmental exposures and tries to predict clinical outcomes from such high-dimensional molecular data. So we obtain biomarkers from different genomes belonging to people and take into account different environmental attributes like exposure to tobacco. And we can then go ahead and fit a Cox survival model, as you see here, and use backpropagation to get the predicted risk with respect to the outcome. Essentially, we're making the survival of certain cohorts of people who have unique biomarkers in their genomes or have certain exposure to environmental effects. We can also run this analysis on huge data sets at scale using TIBCO data science, where we can wire up the analysis to show inside our visual analytics tool. For example, on the top right, we can see the Kaplan-Meier curve, which shows the difference in survival as a function of time. So here, the probability of survival is a function of time with respect to certain cohorts that may have certain genomes or environmental exposures. Now, we can configure all of this inside Spotfire, which calls out to the TIBCO data science modeling at scale on large data. Now, below here, we can also see that our data science platform runs calculation at scale on cluster. And by adding more Spark workers, we can actually achieve massive speed up in getting the results from the analysis. So we scale our data science environment depending upon how quickly we want the results. Now, coming back to this, where we all started on hyperconverged analytics. So we're looking at these different personas and the collision and the convergence between them. So we have the data scientists and the data engineers who are doing data prep or building models inside our TIBCO data science platform. And then they can wire this up into our visual analytics tools, where the business analysts can then gather insights from that model or the model explainability. And at the same time, they can take the model that was developed inside of the TIBCO data science platform and fully operationalize it And this is where the ML engineers come in and build streaming workflows to put the models in operations. And we can see all of this is, again, a loop and a closed loop that I talked about before, where we have this convergence where data scientists and data engineers are continuously working hand in hand with these business analysts, and they're working hand in hand with the ML ops engineers or ML engineers. So to really end this talk, I'd like to touch upon some of the key takeaways. Definitely worlds of analytics, data science, data management, and operations are all colliding and converging. And we here at TIBCO believe that as a data science leader or a practitioner, tools should facilitate your team to work together more collaboratively and enable seamless navigation in the areas of convergence. The cloud vendors also play an important role as they provide building blocks that help enable best of analytics, data science, and data management. So I thank you all for attending this session. Again, if you're interested in learning more, I would recommend you to click on the following links and check out some other cool examples and use cases of hyperconverged analytics and some other customer success stories. And as I said, I do have the breakout room open now. So if anyone who's interested can just come into the breakout room, and I can take questions there. Thank you.